reasonably superficial level, because each one of this merits a talk in its own right. So I would start with what one means by saying a strongly correlated electron system and how this comes about from a natural consequence from, say, the Drude's theory. And then I would run you through the Hubbard model to begin with, and the key concepts behind what is known as Mott physics. And then we move to the phenomena of heavy fermions in solids. This was important once upon a time because of the fact that it was the first system in which superconductivity and magnetism were thought to coexist. It still remains important in the relative context of quantum phase transitions. And more importantly, the area of heavy fermions is also a natural segue into the phenomena of high temperature superconductivity, which would come next. And I do presume that you have many talks which are going to deal with, at least some talks dealing with topology in quantum materials. So I would not do too much of it. But stick to more classical strongly correlated systems like phenomena like colossal magnet resistance, charge ordering, electronic phase separation, and so on, and end with a summary of the kind of experimental probes which I used, why these systems are have been interesting for a long time and continue to be important today, since we are talking about mm, the role of quantum materials in the general area of quantum technologies. One should remember that in many senses, materials is not a separate vertical in the quantum technology domain, but it is more like horizontal because it feeds into all different areas. You need materials to do quantum communications, quantum sensing, and quantum computing. And that is the reason why materials is something which is just not a simple vertical within the quantum technologies domain, but something which is more like horizontal and feeds into all these real world applications. And we'll end with some very open and old challenges which continue to remain ununderstood in this area. So, if one looks at basic solid state physics, and I presume that all of you would anyway have done this into your courses, many of you would still be teaching them. A phenomenal leap of faith when it comes to trying to understand solids was the Drude's model. Now, the Drude's model is effectively a very simplistic one. It looks at a statistical mechanical model of non-interacting systems. But nevertheless, if you, in spite of its conceptually simple nature, it is actually a remarkable feat because what it does is that it gives you reasonably accurate predictions on a number of things. It, for instance, tells you how the Ohm's law comes. It tells you how the Hall effect comes. It gives you a sense of relaxation and scattering processes in solids. It also helps you, at least to the first principle in simple metals, calculate terms like the optical conductivity and so on. Now, so an ultimate classical physics model, the Drude's model. Nevertheless, we know that that's not sufficient, and when one moves from the Drude's model to a more sophisticated description of solids in general and quantum materials in particular, then we encounter what is this classical band theory. So the idea being, of course, that if you have single isolated atoms, you have a well-defined energy differentiated energy levels. Whereas when you all put them all together in a form of a compacted, potentially long range ordered solid, then the overlap between these different energy levels naturally gives rise to a band. Now, within the band formalism, you have read about the Bloch's theorem, which tells you how a periodic potential works, and also the Pauli's exclusion principle, which then dictates how you can actually start filling electrons into these bands. Now, this again is works well for relatively simple metals. But when one moves to more complicated, physically interesting, and potentially useful materials like transition metal oxides or even rare earth compounds, heavy fermions, all of these, then this standard band theory starts to fail. Now, why does it fail? It fails because one has to realize that in a solid, like in everything else in work, in life, it is a question always of energy minimization. And what are the key energy scales in a strongly correlated system? So if you look at the right side of this slide, what I've given is a tentative order of the key energy scales in a strongly correlated system. This is more from a perspective of oxides rather than intermetallics, but nevertheless, it's a useful introductory slide. So, what are the key terms which affect you? So, the kinetic energy equivalent term in a solid is what is known as the bandwidth. So it's typically denoted by W. Some people also call this the one electron bandwidth or the effective hopping integral magnitude. So that basically mimics the kinetic energy part of Hamiltonian. The potential energy part is basically the Coulomb repulsion, or it's called also the on-site Coulomb repulsion, typically dictated by the term U. Now, if you see carefully, both of these are always in similar ballparks. I mean, the range can vary. You can have anything from 2 to 10 electron volt in terms of uh, their effective strengths. And in most strongly correlated materials or quantum materials, the down ground state is predominantly dictated between a competition between these two scales and by which one finally wins over. But these two are not the only two scales of interest. You also have the crystal field splitting energy, which now becomes more important in the intermetallic systems rather than in the oxides. You also have the magnetic exchange energy J, which will influence this. If you're again looking at intermetallics, you have the Kondo scale, which is of relevance. So the emergent properties in strongly correlated systems typically arises owing to a complicated interplay between all these kind of energy scales and as to which one finally wins. Now, the when one moves from a standard band theory to what is a Mott-like system or a Mott insulator system, that basically then is dictated simply by the ratio of U is to W. That means a ratio of the bandwidth vis-a-vis the on-site Coulomb repulsion or the ratio of the kinetic to potential energy terms. And that tells you whether, at least to the first approximation, as to whether the material you're looking at is likely to be a system which will conduct, is a metal, or is likely to be an insulator. Okay, however, even in this term, you will see that there are many outliers, and that is exactly how this field is developed. Like, for instance, we look at systems like nickel oxide, cobalt oxide, vanadium oxide, and so on. These, by simple density functional approximations, were predicted to be metals, but experimentally are known to be insulators. So this is a failure of the independent electron approximation. And so one moves from the independent electron approximation to a more complicated and more accurate description of the solid state systems, especially in terms of transition metal oxides, which is what I'm talking about. One moves to what is known as the Hubbard model. Now, don't worry about the long equation. Here again, the competition is between the first two terms, the hopping integral or the bandwidth, which is now within the Hubbard model formalism denoted by a T, and the on-site Coulombic repulsion, which is the potential energy term, which is dictated by the term U. In addition, you will have other things which come in, like the effective commercial chemical potential, which controls the extent of band filling, and the number operator, which is used in this creation and annihilation operators, this thing. And so basically, if depending upon the ratio of these first two guys, you get all kinds of phases which emerge in solids. So, for instance, if you have a very large value of the hopping integral T, vis-a-vis u. So that means u by t is much less than 1. So as you can see, if the bandwidth is very large, the hopping integral is very large, it basically means that electrons can hop very easily from one side to the other. And so in that case, you basically get weakly correlated metals or things like Fermi liquids and so on. If they are similar in range, then you actually have a very strongly correlated system. You will not then have a simple Fermi liquid formalism working. And what you would get if you look at magnetotransport, electronic transport, or even heat capacity measurements, you will see what is known as non-Fermi liquid signatures. Now, if you go to the other end of the spectrum, which is that your U by T is much larger than 1, that means now your effective bandwidth or hopping integral term is much smaller, whereas your Coulombic repulsion is very, very large, then clearly the system cannot remain conducting any longer. So then it behaves like what is known as a Mott insulator. Some Mottness will be described in the next slide as well. And so this kind of then gives you three broad regions of a rather simple phase diagram. However, there are more terms which can add into the equation. So like as I said, in intermetallic systems, you would also have things like the crystal field splitting, which adds in. If you're looking at oxide systems, things like high value of spin orbit coupling will then be a perturbative term. So we would also have these second order terms which play influential roles, right? And so this is not new. John Hubbard discovered or put forward the Hubbard model, I think soon after the Second World War, and it was proposed independently also by Kanamori and others slightly later. Now, this remains an important cornerstone when it comes to the theoretical description of the physics of many of these systems. Now, when one moves from the Hubbard model, which is still within the band model, to a system of localized moments, then one talks in terms of what is known as the Mott-Hubbard mechanism. So here we are looking at basically the third category in the UT phase diagram. That means you have U by T being much larger than 1. And so what basically happens at that case, at very large U, your density of states splits into what is known as a lower Hubbard and upper Hubbard bond. And you have an opening up of a gap exactly at the Fermi level. So what that means is that though in the absence of correlations, you would have expected this system to behave like a metal. These strong correlations result in a gap at the Fermi level, and so you are left with often weak and often reasonably robust insulators. And these insulators are known as Mott insulators and are extremely important in areas as diverse as colossal magnetic resistance to high temperatures for conductivity. For example, there are a few of these classic Mott systems which are known here, and what this Mott-Hubbard mechanism now explains the physics of systems like nickel oxide and so on, which otherwise should have been a metal, but now we know that is an insulator. And this is a consequence of the strong electron correlations that exists within these systems. Now, so what I've told you so far is the basic Hubbard model and the emergence of Mottness on how electron correlations can give rise to insulating ground states. Now let us move to a slightly different area, which are intermetallic metals. Okay, and this region, and this the story of this really starts with what is known as the discovery of the Kondo effect in the early 1960s. So what they were trying to do was to look at dilute magnetic alloys, which basically means that you have a metallic system, like say copper, and then you dope it with small amounts of a magnetic impurity. So like could be something like iron or manganese and so on. Now, when that happens, what they saw was that at low temperatures, you had an upturn in the effective resistivity, and they also saw an effective screening of the magnetic moments by the surrounding cloud of electrons, and that is what is known as the Kondo effect. It's a very important effect in the terms of the intermetallic systems. It is less relevant, of course, in terms of oxides. And the Kondo effect is an integral component of all heavy fermions. And not only can we look upon these individual Kondo scatterers as being sparsely populated in space, but you can also, at reasonably large magnetic impurity levels, have a lattice purely made up of these kind of Kondo singlets. And what this does is to give rise to a whole set of new phenomena when it comes to strongly correlated physics. So, for instance, you know that the electrons have an effective mass, and in these strongly correlated systems, the effective mass can be as large as 3 orders of magnitude greater than the bare electron mass. And this is something which is typically used calculated using methods like specific heat. And you know, a large value of gamma, for instance, tells you that you have a very large effective mass. So that means an electron appears to be 1,000 times fatter than what it actually is. It is not that the electron mass is changing. It is just that the interaction with its local environment makes electron movement extremely sluggish, and that is at the heart of what is known as heavy fermions. Hence the term heavy in the fermionic, which is used as an adjective in front of fermions. Now, there have been over the years a large number of prototypical systems which have been important in the context of heavy fermions. For instance, cerium-11 was probably amongst the earliest. And then there are systems like cerium-2 copper-2 silicon-2, which turned out to be the first magnetic superconductor, albeit with a low transition temperature. Uranus platinum 3, cerium copper to silicon 2, ytterbium rhodium to silicon 2, and so on. So these are, at least for those who would be slightly familiar with the area of quantum physics and heavy fermions, are superstar material systems within this area. And the heavy fermions though they are now currently a bit out of fashion, a lot of the physics, at least a significant part of the physics, appears to be reasonably understood. Nevertheless, it had an extremely rich phase diagram. You had all kinds of behaviors in it. You could see magnetism, you could see superconductivity, you could see well demarcated Fermi liquid regions, non-Fermi liquid regions, and so on. And in many senses, it is the real precursor to the onset of heavy ferment superconductivity, which then relied on a lot of these concepts to explain what is happening in the heavy ferment superconductor in the high temperature superconductors. Now, if you look at the heavy ferment systems, primarily again here you are talking about two energy scales which competing with each other. Okay, the first, as I said, is the Kondo effect. What it does, it has a functional form like this. You don't need to worry about the functional form. But what the Kondo effect is trying to do is to use a cloud of electrons to shield the magnetic moment. So as you can imagine, the end goal of the Kondo effect is to try and deliver a non-magnetic ground state. Okay. And on the other hand, it has a competing effect, which is known as the RKKY interaction, which is a form of a magnetic exchange. So magnetism operates through exchange interactions, which can have different forms. You can have the direct exchange, where two spins directly talk with each other. You can have the indirect exchange, which is multiple fold. You have super exchange, where they talk through a ligand. You can have the RKKY interaction, where they talk through a sea of conduction electrons. Now, since these are metallic, typically 4F5 kind of metals. So the Archive interaction is naturally present in these systems. So what you have is you have local moments, and one local moment tries and talks to the next local moment by polarizing the sea of conduction electrons in between. Now, what this is trying to do is to give rise to a magnetically ordered ground state. So as you can see, there are two competing interactions, one which wants a magnetically ordered ground state and one which does not want a magnetically ordered ground state. And so at lower value, so this is known as something known as the Donish phase diagram, which actually gives you a rather nice a description of this. So what you have here in the dashed red line is the functional form of the RKKY interaction. And as I said, that would like to give rise to a magnetically ordered ground state. And so this thing in green is thought to represent a magnetically ordered ground state. And on the other hand, this thing in blue is the effective strength of the Kondo interaction, which wants to kill magnetism. And the point at which they both meet is when the magnetic transition temperature now goes to absolute zero. And this is at the heart of what is typically known as a quantum phase transition. A quantum phase transition is one where you have a putative phase transition happening as t tending to zero. And it is important because a lot of the consequences of that kind of phase transition are seen at much higher temperatures. Now, so here I have already mentioned a few, so I don't need to go necessarily. This is another class of materials which were very popular once upon a time. I had worked on this during my postdoc days. I think probably Manoj also worked on some of this. That is uh, the cerium rhodium indium 5 or the cerium cobalt to indium 5 family. Now, sorry. So moving from the heavy fermions and bare Kondo physics part to high temperature superconductivity. So what I am talking about here is the cuprate phase diagram. Okay, so the as you know, superconductivity was discovered with by Kamerlingh Holmes a little over 100 years ago, with the onset of superconductivity in discovery of superconductivity in mercury. Mercury, because mercury could be refined to a very high purity even during those days, and it shows you a superconducting transition at around 4 Kelvin or so. Now, the high TC the heavy fermion superconductors are typically low TC superconductors. You know, they have magnetism in their vicinity, in the neighborhood. So, and the magnetic order, the superconducting transition temperatures can vary from a few millikelvin to maybe a few tens of Kelvin. I don't think there is anything which exceeds 20 Kelvin or so. Now, in the late 1980s, Bernards and Mueller discovered superconductivity in a lanthanum barium copper oxide system. The first discovered superconductivity was with a TC, effective TC of 35 Kelvin, but it is still a high temperature superconductor. And within a year or two, people took these transitions to much high temperatures. The most popular one which you would hear about is something called YBCO, ytterbium barium copper oxide, which has a transition temperature, if I remember correctly, of 92 Kelvin or something. It's slightly above liquid nitrogen. Now, now, one should remember that this is a very different material class. You if you're looking at the heavy fermions, you're basically looking at ordered or side diluted magnetic metals. Here we are starting off with a robust Mott insulating oxide. Okay, so so if you look at the phase diagram here, I'm not sure, Manoj, can you see my arrow?
It's not. Yes, sometimes it is visible slightly.
Is it visible
No
now?
moves are. Mm,
Is it visible now or is it visible now?
Now it is visible.
Okay, so because I have two screens in front of me, so now it's visible, right?
Okay.
So
Yes, sir.
you can see this. All right. So this is the generic cuprate phase diagram. So these materials start off as being antiferromagnetic Mott insulators. Okay, so which means so this is the y-axis is temperature, the x-axis is actually the doping in the copper oxide plane. On the right here is the bare structure of a lanthanum cuprate system. I mean, from one family to another, there would be small differences, but the takeaway message here is that all the action happens in this 2D layer of copper oxide. Okay. And to begin with, there are no holes in this copper oxide layer. And so at that point, the system is an antiferromagnetic insulator. So you would have a phase transition happening here as you reduce the temperature. At the higher temperatures, it's a paramagnet. And now, as one starts doping holes in this copper oxide layer, you will see that the antiferromagnetic transition goes down, 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 and down. Beyond a point, there is no measurable magnetism. And then you also see the emergence of what is known as the superconducting dome, which means that at some point, this system starts to become superconducting, reaches a maximum TC at some value of hole doping. This would change from one material system to the other, but it is often of the order of zero point 0.2 or so on. And this is known as, so the lower region is typically called the underdoped region of the cuprate phase diagram. Then this region is known as the optimally doped region of the cuprate phase diagram, and the higher region is known as the overdoped region. So because at some point the superconducting dome also crashes, you have no superconductivity left, and then one is effectively left with a standard Fermi liquid. Now, the interesting thing here is that if you look at almost all unconventional superconductors, you look at heavy fermions, you look at cuprates, you look at the iron pnictides, you will see that there is a remarkable amount of similarity in the way that the phase diagrams look. And that kind of tells you that there is the underlying physics probably is quite similar. There's also a very interesting region here, which is known as a pseudo gap. One still does not fully understand the pseudo gap phase. This is a system in which this is a region of the phase diagram in which you see the emergence of what looks like a gap in the Fermi surface, and this can be then gauged through multiple techniques like RPS and even the standard electronic transport measurements. Now, the one of the potential scenarios which people are quite fascinated by is the possibility that the superconducting dome actually arises due to a quantum critical transition associated with the pseudo gap phase. Like for instance, if this line would have gone down, down, and down, it would have hit zero at somewhere around this point, which is where you also have the largest superconducting transition temperature. This has been a popular, very popular means of discussion. There are many experimental reports which support this observation. There are some experimental reports which do not support the observation. Nevertheless, this is something which still still is investigated in a lot of detail. The other thing which combines the physics of many of these unconventional superconductors is the nature of what is known as the pairing symmetry. Okay, so if you look at the pairing symmetry, is it an isotropic S wave like one, or is it an isotropic T wave like one? Is something which is of extreme use. Typically, all unconventional superconductors, which means these are superconductors which have magnetism in its vicinity, are D wave like. So that is true for many of the heavy fermions. That's true for sure for the with the cuprates, and it is also true for many of the pnictides. Okay. Now, so as I said, there is no full consensus regarding the pairing mechanism. And is it clearly in the conventional superconductors? The simple pairing mechanism is phonons. Here, it could be a combination of phonons and magnons, or something which we have still not fully understood. Now, so I've talked already about some of this. We have a crystal structure is perovskite derived. As I said, it is the copper oxide planes which are separated by charge reservoirs, which is the place where all the actions happen. The parent compound is lanthanum cuprate. You start with a spin half, and you start doping holes in this. And when one dopes holes and one gets the superconducting phase, there is a lot of action happening in the electronic sector. And there are, for instance, something called the formation or potential formation of the Jang-Grant singlet, and so on. So let me not go into too many details of this. As I said, this is a talk or two, or maybe even a course by itself. So what are the different kinds of pairing mechanisms which are proposed? In a simple superconductor, the pairing mechanism is simply phononic. Now, a different version of this has also been proposed to be which is known as a bipolaronic one. It's been proposed for heart disease as well, though most people now believe that it is not true. You can have charge fluctuations, which means that you have a dynamical fluctuating charge in orbital order, which can also, in principle, act like a glue for the Cooper pair formation. So, as you know, in superconductivity is driven by Cooper pairs. These are two electrons which typically would not like each other because of the inherent Coulombic repulsion. But when you have the formation of a Cooper pair, you need to have some other glue which makes the formation of a super pair energetically favorable. Now, the question is, what is that glue? In a simple superconductor, that glue is phonon. In some superconductors, it can be charge fluctuations, though this still remains debated. The resonant valence bond model, initially proposed by Anderson and, of course, by G. Bhaskaran from India, which he has been one of the pioneers of this kind of model, is also an influential model, though there are some uh, systems where it may not necessarily work that well. Till date, probably the most successful model is that these are the formation of copper pairs is enabled by the presence of spin fluctuations, which are always there in the vicinity of this phase diagram. So these are all superconductors in which magnetism is prevalent, and that these spin fluctuations then act like the bosonic glue to hold these fermions together. Okay. Now, I believe that you have had many talks on, or certainly some talks on topological quantum matter. So let me not go into too many details of this. You would have already heard some of this. If not, you will be hearing this in other lectures. This is again a relatively newer entrant into the area of strongly correlated systems. By newer, I mean about say a decade or so. Till then, topology was something which only the mathematicians did to talk about cute things. And now we realize that in solids, these are extremely important. There's only one real key takeaway message, and that is the bulk boundary correspondence. Is that you, in systems which are topological, you would have density, electronic density of states on a surface state, which would be very different than the electronic density of states in the bulk. And that is something which was predicted by Fu and Ken in 2007. It was observed first by Shen's group by using angle resolved photoelectron spectroscopy to 2009. And so now, yeah, I had miscalculated. Now we are almost 20 years into the onset of the era of topological superconductors. Uh, Spin liquids and Kita materials are closely related, while and Dirac semi-metals directly arise from topological super insulators. And topological superconductivity is another very interesting area, relatively less looked at in comparison with standard topological electronic materials. But the key here is that the topological superconductors are thought to host what is known as Majorana zero modes at the boundaries, at the surface boundaries. And this is something which has a lot of relevance, or is thought to be extremely important in the area of quantum computing going ahead. So if you would know that Microsoft's quantum computing platform was called Majorana, and that has been the subject of some controversy. They showed some qubit operations and so on, but it is not terribly fully accepted by the community yet, because they were using, they're trying to use this attribute in superconductors to try and do qubit operations. Now, another very interesting system which so far has had relatively less direct application, but is at the heart of a lot of this strongly correlated physics, is the physics of what is known as quantum spin liquids. So if you look at quantum magnets, they exist in different phases and forms. Diamagnets and paramagnets, and then if you have the exchange interaction winning over the effective thermal energy, then you have a magnet which has a long range ordered state that could be either ferromagnetic like if the exchange integral has the positive sign, it could be antiferromagnetic like if the exchange integral has a negative sign, and it can be a combination of all of that. And so you add in disorder, you get something like which is almost a glass like and so on. Now, by definition, a quantum spin liquid is a system where you have very large values of J. That means that the magnetic exchange strength is significant, and in normal state, that system should have just shown you a plain vanilla para to ferro or a para to antiferro phase transition. But very often, the structural motif within which this magnetic state operates, which can be a triangular lattice or a Kagome lattice or a paraclo lattice and so on, then imposes what is known as geometrical frustration. So what it does is that it does not allow these spins, which have a large J talking between them, to settle into an ordered ground state. Now, this happens especially for low spin systems. Spin half is the best place to look for quantum spin liquids, and also low dimensional systems. So, systems which are inherently 2D, or even if they are not 2D, if their physics is 2D like, that means they are layered and there are only some magnetic layers in between which where all the action is happening. Then in this case, you have what is known as a quantum spin liquid. So these are systems where you do not have magnetic order, but a lot of strong quantum fluctuations will exist till from the lowest temperatures to reasonable temperatures. And now the reason why this is important in the context of quantum materials is, of course, because you have a lot of interesting physics happening here. One of the most important emergent excitations here is something called spin-ons. Spin-ons are basically so if you look at a simple electron, an electron has charge, and an electron has spin. Now, spin-ons were first proposed actually by P.W.D. Anderson in the early days of the cuprates, where he said, what if you have a quasi-particle which only has a spin degree of freedom of an electron? Okay, and so what it basically did was, we know that an electron has a spin and a charge. What Anderson proposed, it was the existence of quasi-particles which held these two things separately. So you could have a quasi-particle which only has the spin degree of freedom, so that would be called a spin-on, and you could have a quasi-particle which would only have the charge degree of freedom, and that would be then called a holon. And these have been talked about. We have all, I mean, including me, I think probably Manoj too, have done some work in these areas, trying to see whether you could really catch hold of spin-ons by doing magnetotransport and so on. And that still remains. And quantum spin liquids are thought to be ideal test beds to look for spin-on-like signatures, and many of them have actually been seen. Okay. Then there are issues with emergent gauge field and gapped quantum spin liquids and so on. So quantum spin liquids is, again, the reason I'm just mentioning this out here is so that one is aware that this is an area of extreme interest. There are lots of uh, um, potential avenues to do work in this area, both from the especially from the experimental point of view, because the theory, I think, has to some extent been done. And now the problem is this, that if you are saying that you have a system which does not have magnetic order, then how does it differ really from a paramagnet, and what are the experimental tools you would need to use to say that this is a spin liquid? So there are many tools which are now well known. Like, for instance, if you do magnetic scattering, you will see a very large diffuse amorphous light background. In neutron scattering, you will not see any magnetic bragg peaks till the lowest temperatures. If you do inelastic neutron scattering, you would see a continuum of background excitations, which is basically, it's not a real background excitation, but it is a broad spin-on continuum. You can do specific heat measurements, look at the gamma T term. You can look at something now called as the Wilson anomaly ratio and so on. So experimentally, there are quite a few tools which are currently available for us to get a sense of whether which systems are quantum spin liquids, and how does one quantum spin liquid differ from the other. For instance, are these gapped quantum spin liquids, are these non-gapped spin liquids? And now you have, of course, the onset of an area called as chiral spin liquids and so on. So there's a lot of interesting physics happening in this. And the reason why people are interested in this, because of the fact that you have the possibility of getting emergent excitations like spin-ons and so on, which people think are useful platforms to look at very specific quantum technology applications like quantum memories and so on. So, no, I have so far talked mostly about superconductivity and its surrounds. There are a few more properties of extreme interest which I would like to briefly touch upon. And one of them is the phenomena of what is known as colossal magnetoresistance. Slightly old now, nevertheless one which actually sits in many of our devices. So if you take a metal and you measure the resistance and apply a magnetic field, you'll see a magnetoresistance. The resistivity changes, right? In a metal, it simply happens because the electrons are now going on so spiral paths, and so it effectively the resistance changes, and you have the Lorentz force giving rise to a finite resistance. Now, there in that case, the magnetic resistance is positive. That means by application of a magnetic field, the resistance slightly increases. But there are many other systems where the resistance change can be in the opposite direction. And one of the most important ones is a class of materials called as the manganese. So these are basically different kinds of manganese oxides. A generic phase diagram is shown here. I would just like to remind you about the couplet phase diagram earlier. This works in kind of similar fashions. Like for instance, you start off with a Mott insulator. You whole dope it, so you dope charge carriers into the magnetic lattice, and then that Mott insulator then transforms to a ferromagnetic state. In the couplet space diagram, you are having that Mott insulator transform to a superconducting state. But here you have a ferromagnetic state shown here in red. Now, within this ferromagnetic state, you actually see a very large magnetic resistance. The magnetic resistance can be as large as I've written here, 10 raised to 6. So in this case, the magnetic resistance is negative. So what happens is that you have very large spin fluctuations in these systems, and that is a primary cause of resistivity. So the moment you apply a magnetic field, it very strongly suppresses that spin fluctuations, and so the resistance drops. So in these systems, which are metals of some kind, they are dirty metals, not clean metals. The magnet resistance has a different sign as compared to that in the simple metals. In the simple metals, the magnet resistance is positive. In the CMR materials, the magnet resistance is negative. Now, I don't think I have enough time to go through what all of this means. There is a very interesting mechanism which gives rise to ferromagnetism in the case of manganese, and that is known as Zener's double exchange. And this basically happens because in the case of manganese, for instance, you have, if you're starting with the parent compound, which is LeMnO3, manganese is always in 3 plus. The moment you start doping holes, you will have some of the manganese sitting in 4 plus. And this is an indirect exchange system, which means that you have the two magnetic ions being separated out by an oxygen ligand. And the moment you have a few Mn4 pluses, then double exchange can kick in, and you basically have a virtual hopping of an electron through this ligand, and that virtual hopping then gives rise to both ferromagnetism as well as metallicity. So your system basically transforms from a insulating antiferromagnet to a conducting ferromagnet. And within this conducting ferromagnet, you still have a lot of spin fluctuations. And so when you apply a magnetic field, the spin fluctuations are strongly suppressed and then gives rise to magnetic resistance. So if you look at so magnetic resistance has basically progressed in three phases. The earlier days of magnetic resistance was looking at magnetic resistance in simple metals. There is I think whose book is it? Manoj will probably remember. There's an old classic textbook on magnetic resistance in metals. And then we had the onset of the era of GMR or giant magnetic resistance. This is the phenomena for which Fert and Grunberg won the Nobel Prize in '86, which are basically multi-layer like arrays. And there you had, conventional GMR, which would basically mean you could have magnetic resistance of up to 100%. Now, once that was done, this was in the early 90s when people encountered the manganites, where you could have an MR value of up to 10 raised to 5, 10 raised to 6, and so on. And that is when, since you had already used the term great in the term in the context of, or giant in the context of giant magnetic resistance, then these materials were now called collusive magnetic resistance materials. So even at this point, this seems to be the class of materials which shows you the largest value of magnetic resistance in the vicinity of room temperatures. And this has a number of potential application areas, most particularly in the area of magnetic sensors when measuring magnetoimpedance sensors and so on. Now, looking at the time, let me not go through. Okay, I'll maybe just go through charge order and leave the other part. So there is in many of these systems another very important phenomena which happens, and that is known as charge ordering. So if you just remember what I said in terms of the colossal magnetoresistive magnetites, you start with that is these systems here, the phase diagram here. You know, you start with a Mott insulator, you start doping holes, and then you move from an antiferromagnetic system to a ferromagnetic system. What happens is after a point, when you have hit 0.5%, 50% hole doping, and even at the slightly overdoped regions, you now get a completely different phase. The system now transforms from being a ferromagnetic metal to an antiferromagnetic insulator again. And this is not a normal insulator, but it's a charge ordered insulator. So what does that mean? So what this basically means is that if I have a neutral chain of atoms like this, right? So they are all equidistant from each other. There's nothing much happening. The moment I put charges on this, and now consider that one of them is an Mn3 plus and one of them is an Mn4 plus. So you basically have a charge differential of one electron between the two lattice sites. Then you have, in principle, the possibility of what is known as a site-centered charge order. So basically, it's just Coulomb repulsion at play, and you have something known as dimerization. Two of these guys come closer to each other. Okay, so like you form two units here, another two single double unit here, another double unit here, and so on. So this is known as a bond-centered chain order. So when you have the charge ordering in systems like manganetes, you basically have the local electronic structure basically transforms to something like this. And so you have a combination of what is known as bond plus site centered charge order. And what this does is that it can also give rise to a phenomena of ferroelectricity. So ferroelectricity is basically just the long range ordering of electrical dipoles within a solid. Now, what if you can look at these green and yellow units together, put together, this is an electrical dipole, right? So this is one electrical dipole, this is another one, this is another one. And then when all of them line along a solid, you also have the emergence of finite electrical polarization. So now, in addition to magnetic ordering, you also have electrical ordering, and the combination of magnetic and ferroelectric ordering gives rise to a different area of research altogether, which is known as multiferroics. So that means you have more than one ferroic orders in the same material. So this again has been an interesting area for quite a long time. I would probably not go into electronic phase separation because the physics of this is interesting in the terms, especially of both the cuprates and the magnets, both of which I have talked about, especially when it comes to describing magnetoresistance. But let me skip that. Now, I've talked about a lot of materials. How does one look at many of them? How does one measure properties of strongly correlated systems, especially when it comes to looking at energy and momentum slices? A lot of the action happens at the level of Fermi surfaces. So the indirect probes of looking at it are things which people like me and Manoj do, which is looking at heat capacity, looking at magnetic resistance, looking at Hall effect, and so on. But now the onset of a more sophisticated large-scale facilities has given rise to a whole set of experimental tools which allows you to look more directly into the band structure of these systems. So like for instance, you have angle resolved photoemission, which directly maps out the Fermi surface for you. And this is something which is very important, especially now in the context of topological systems where RPES is a technique of choice to measure or to map the Fermi surface of materials. If you do not have the luxury of going to a large scale facility, but you want something which can be done in the lab, then you have techniques like the scanning tunneling microscopy or spectroscopy, which does not give you all that an RPS measurement does, but it still gives you a real space mapping of the density of states. It can help you visualizing things like charge orders, fermions, vortex cores, all kinds of things. If you have scattering techniques, you can look at things like Gauss spin rotation, which gives you the distribution of the local magnetic field. MUSR, for instance, is an extremely important technique when it comes to looking at quantum spin liquids. Neutron scattering remains a very popular technique when it comes to magnetic solids. If you're looking at charge and orbital ordering, there the technique of choice would be to use something known as a resonant X-ray scattering. Unfortunately, not very easily available in India, though there is, I think, one beamline which is being set up, which has been set up in Indus. And then there are things like quantum oscillations and so on, which can unfortunately only be really done well if you have large single crystals. Let me not talk about Moires and ARPEs. So I have already talked about quantum phase transitions earlier when I was talking about the heavy fermion systems. So basically, I just want to re-emphasize that across different material classes, be it cuprates, be it heavy fermions, be it pnictides, a lot of the physics appear to be similar. That means you have a superconducting ground state closely tied with a potential quantum phase transition. Now, what that does is that it gives you, at reasonably large temperatures, a bunch of non-Fermi liquid signatures. So, for instance, you have a quasi-linear temperature dependence of the resistivity. In a simple Fermi liquid system, it should have been T square. You have a log T kind of dependence in your C by T. You have an effective temperature independent magnetic susceptibility and so on. So these are telltale signs of quantum phase transitions and criticality, and something which is very important. Now, why are we talking about a lot of these things? Some of these things are known for quite some time. Like, where is these things important? Squid magnetometers is one. Of course, we use this in real life. I have a magnetometer in my lab. People use magnetometry when you're looking at biomedical imaging for geophysics, all kinds of things. Josephson junction circuits, again, now is extremely important in the context of superconducting qubits and so on. Medical imaging requires many of these kind of materials, especially alloy-based superconductors. The area of topological quantum computing is an extremely interesting one. So if you look at quantum computing per se, there are three major hardware platforms. You have the superconducting qubit-based platform, you have the uh, ion trap or cold atoms-based platform, and you also have the photonic-based platform. Now, within the superconducting qubit-based platforms, they're typically transmon or fluxonium kind of qubits. IBM uses this in their quantum computers. The problem appears to be hitting a glass ceiling in terms of the number of qubits which one can successfully operate. Now, many people think that topological computing can give rise to an edge, especially when it comes to what is known as fault-tolerant qubits, because the effects of things like scattering are much less pronounced in topological surface states. As a matter of fact, theoretically, backscattering is completely ruled out in topological surface states. So that is another a big area of interest, because it is one thing to make a superconducting qubit-based quantum computer. The fact remains that quantum error correction is a very important part. There is a lot of errors which happens during the course of this probabilistic computing. And people think that in topological superconducting based quantum computers, this error correction will be minimal. You would not require, so there is a theoretical promises of exponential error correction as one increases the number of qubits. And then, of course, other accelerator uses like accelerators and fusion and so on. So here is this thing of high TC superconductors. Let me quit that. So what are the kind of challenges which we still have when one, so the area of strongly correlated systems is very old. In the recent past, we have started calling it quantum materials because it is more fashionable, but this is in a very old area. And in spite of the fact that people have been working on it for close to 80 odd years, there are a large number of even older problems which remain completely unsolved. So, for instance, one would be the pairing mechanism in cuprates. The cuprates were discovered in the mid 80s, and now we are 40 years down the line. We still don't understand the real pairing mechanism in cuprates. Is it spin fluctuations, charge fluctuations, something which we have completely missed out, a combination of all of this and so on. Then similarly in both the cuprates as well as the heavy fermions and the nictide superconductors, there is the concept of a pseudo-gap phase. Now, what is a pseudo-gap phase? Is it a real phase? Does it necessarily have well-defined phase boundaries? How does the pseudo-gap phase give rise to a superconducting phase? These are things which are again not understood enough. As I was saying, many of the superconducting states have a hidden quantum phase transition in its vicinity, and that then gives rise to what is known as a strange metal phase. So, for instance, you can have a linear resistivity change, whereas it should have been quadratic in the case of a simple metal over many decades of temperatures. So, how does this happen? There is no real microscopic theory which is universally accepted in this area. I was talking a bit about quantum spin liquids. Now, quantum spin liquids have many different flavors. One of the very important areas of research is looking at quantum spin liquids in two dimensions. Now, do the real um, 2D materials actually host a quantum spin liquid state, or is it that we are just saying a quantum spin liquid because we have not gone low enough in temperatures where they will actually order? So this is a very important systems. Moir systems I have not touched upon, so let me talk about it. And then also there's a lot of interest in non-equilibrium systems. That means you generate by an external perturbation a transient phenomena. Examples can be like photo-induced superconductivity and light-enhanced superconductivity and so on. And that then gives rise to a number of very different phenomena which are not typically available in equilibrium systems. So non-equilibrium systems have their own set of very useful physics associated with it. And with that, let me summarize because I think I have gone out of time. I was hoping to keep them short. So I will just leave this for you to read, and if there are a couple of questions I can answer before moving to the next talk.
So there are questions actually. From the chat box, I can see.
Okay, can you please read it out to me? I can't see the chat
Yes,
box.
sir. Yes, sir.
Stop
I'm
sharing.
just so from Dr. Prahlad Rao, he was not clear about phase transition. Towards the
Okay.
starting of the slides or the lecture, what phase type of phase transition was discussed? I think he was not completely clear.
Okay, I would have mentioned phase transition quite early on. So, so what is a phase transition? I mean, at the simplest level, it is like water to ice, or ferromagnet to antiferromagnet, or metal to insulator, and so on. Any transition from one kind of magnetic or electronic state to another kind of electronic state or magnetic state, driven by an external perturbation, which could be temperature, pressure, electric field, magnetic field, and so on, and which can be characterized using a set of well-defined critical exponents. That is how you would describe a standard phase transition. What else, Manoj?
Okay, so there is one more from Devansu. In different parts of physics, experimental results were observed prior to the theory behind it.
Hmm.
In some cases, the theory came prior to experimental one. In other cases, the other way around was true. In the context we are discussing today in the class, which was the case? Did we have the theory prior to the experimental observation or vice versa? For, let's say, some of the materials we discussed today.
Yeah, okay. I can quickly go through two or three. Like for instance, if you look at the Kondo effect was first seen experimentally. Then
Yes.
Kondo came up with a theory to explain the Kondo effect. If you look at the Donesh phase diagram actually predicts the quantum critical point. But here the theory came first in 1977 itself, whereas the first robust proof of quantum criticality experimentally came in the early 2000s, right? Using ytterbium sodium 2 silicon 2 and so on. Now, when it comes to high temperature superconductivity was an experimental discovery. Berners and Mueller were both experimentalists who discovered high TC2 superconductors in 1986. Now, a lot of the cuprate physics, like for instance, many of these pairing mechanisms followed after that. So, topology predominantly theoretical driven. Experiments are still playing catch up. A lot of topological work happened first in theory and much later in experiments. So, quantum spin liquids also, it was theory driven. Theory came first, experiment came later. Colossal magnet resistance was experimental driven. The first report of CMR by the um, Japanese groups came first, and the relevant theory associated with it came later. So, in that sense, I mean, there is no fixed rule. As you can see, I'm going back and forth. So, in some cases, theory drives experiments because the experimental techniques or facilities were often not good enough to prove or disprove a theory at that point of time. In many cases, the experiments drive theory. You see a phenomena, and then the theorists come together to try and fix up a model for it. And if you look at superconductivity, for instance, it has been 40 odd years, and theory is still behind experiment. Theory has still not managed to put together a theory which explains everything in one coherent package.
Okay, sir. I think this addresses the concern. One more question repeated by Bhavna Mahesh and then Dr. Venkata Ramana. How is Mott insulator affected by magnetism?
Okay. See, a Mott insulator is predominantly magnetic. How is it affected by magnetism? For instance, there are cases like, for instance, if you look at charge ordered Mott insulators, where if you apply a large enough magnetic field, you can actually melt the insulating state. And so you can actually have, on the application of a magnetic field, breakdown of the Mott picture and move from a Mott insulator to a strongly correlated metal. So magnetism is intimately connected with Mott insulators in many cases, and though in some cases the insulating state can be melted, in many cases they still can't be melted using laboratory magnetic fields.
Okay, sir. There is one more from Mr. Durgesh. Uh, Fragile superconducting qubits in comparison of other type of qubits.
How what?
Fragile.
Fragile. Okay. Okay. So that is an interesting question. Uh, it depends upon. So it depends upon how you. To be really honest, it depends upon how you define fragility. Okay. If you look at superconducting qubits, now uh, they are extremely susceptible to temperature fluctuations. Okay. Now that is the reason why you need to, if you look at the materials with which these qubits are made, they have transition temperatures. I mean, people make it with niobium and these kind of metals, which have reasonable transition temperatures like 4 Kelvin, 4.5 Kelvin, 6 Kelvin, and so on. In spite of that, to do qubit operations, you actually need to go down to millikelvin. The people typically like to sit at around 10 millikelvin to do qubit operations. The reason being that the coherence time associated with superconducting qubits is relatively small, and you need to have a long enough time to be able to do logical gate operations, and that you can realistically achieve only by going to much lower temperatures. So in that sense, superconducting qubits are more fragile than, for instance, ion trap qubits. Ion trap qubits have much larger coherence times, and once set up, in some senses, are less fragile, if you can call it that way. However, superconducting qubits have an advantage. As compared to ion trap qubits, it is probably far more scalable. So people think that you can scale, it has already been scaled up to 100 odd qubits plus. And not only that, now people also realize that one can actually, if you make, say, 100 qubit system and another 100 qubit, so they call it chiplets. So you make a 100 qubit chiplet, you make another 100 qubit chiplet, you can now stack them together to make a much larger system. Many of these things are not that straightforward when it comes to ion trap computers, because you basically need to have a chain or a lattice of ions trapped, and you should be able to do independent qubit operations. So that's tricky. So there are pluses and minuses to both, and that is the reason why, if you look at how both academic research as well as industrial research is happening, there are different parties who are investing in different platforms. Google and IBM want superconducting qubit platform. There are others like D-Wave and IonQ and so on, and Honeywell, who are investing in an ion trap platform. The Canadians, Xanadu and so on, are investing in photonics platform, because none of them are terribly sure which is the one which will finally win over. So they're taking an educated guess and betting on one platform or the other. We don't know, maybe 20 years down the line, a different platform might win over all of these and can become the standard. So it's difficult to say. But as far as the fragility is concerned, I would say that superconducting qubits are more fragile as compared to ion trap, but are also, so that is a disadvantage, but is also more scalable as compared to ion trap. So that is an advantage. So you have to mix and match.
Sir, there are queries coming up. 2, 3 more queries, but I think we can take some break here, and queries can be addressed over after the lecture, the second lecture.
Sure. So how many minutes of break do I have? 5 minutes?
5 minutes, 5 to 10 minutes, up to you, sir.
So
As you like.
I'll just take a bio break, and I'll then do the next talk. Huh?
Yes, sir.
Okay.
Okay, thank you.
So I'll just remain logged in. Okay.
Yeah, it will be better, sir. Welcome back, sir.
Thank you, Mike.
Okay, sir. So we can start the talk, and I suggest to the participant, please keep posting the queries. We'll address those towards the end of the lecture.
So let me. So can you see the slide?
Yes, sir. It is perfectly visible in full screen mode.
Okay. So now let me come to the second talk. So since Manoj had asked me to give one on a more general one, so I gave the early one on strongly correlated systems. And the second one is an area which is relatively newer, and that is called magnonics. And so I actually have a lot of slides here. I will stop halfway through because I think we will not have more time than that. So so let me begin. And so this is the outline of the talk. So I would want to basically talk about what is magnonics, so the some of the history associated with this area. The I would want to introduce the concept of what is known as spin currents. We are all aware of charge currents when it comes to resistivity and conductivity of solids. So I want to introduce the concept of what is known as spin currents and how they can be detected and generated. Then the problems and potential artifacts which arise when one looks at the generation and manipulation and detection of spin currents, and some potential use cases going forward. And we have ourselves been doing a fair bit of work on magnetic spin currents in quantum materials, and so that was the second part of my talk, but I don't think I will have the time to touch upon that. So first to get the nomenclature in place. Okay, so what is so this is just to tell you what different areas mean. So when one talks about electronics, one is basically talking about the transport and the manipulation of charges in solids, right? So your our conventional electronic devices work because you actually have a physical transfer of charge from point A to point B, and devices in terms of diodes and transistors and op amps and so on and so forth. Now, the electrons have, in addition to charge, it has a quantum mechanical attribute, which is the spin. Right? All electrons have a spin. And in traditional electronics, the spin degree of freedom is not taken into consideration at all. And so the area of research where one tries to utilize that spin degree of freedom in potentially useful devices is known as spin electronics or spintronics. So I believe you've had or you will be having a few talks which concentrate on spintronics. Now, the another term to bear in mind is calorimetry. So, what is calorimetry? Calorimetry is basically the measurement or the investigation of the heat of chemical reactions or physical processes. So, this is where you are looking at heat transport in systems. So now you have electronics, you have spintronics, you have calorimetry. So the first combination area is known as spin caloritronics. So what is spin caloritronics? Spin caloritronics is the transport or manipulation of the charge and the spin degrees of freedom via heat. Okay, so that is the area of spin caloritronics. Going forward, I will tell you a bit more about it. And closely related to that is the area of magnonics. So magnonics is basically the transport or the manipulation of magnons or spin wave quanta. So if you look at the kind of quasi-particles which can exist in solids, of course, electron is an elemental particle. You have phonons, which are basically quasi-particles and are quanta of lattice vibrations. Similarly, you can also have magnons, which are the quasi-particles of spin wave excitement. So if you have a magnetically ordered solid, then you can actually excite what is known as a spin wave quanta in a solid, and the area which deals with the generation or excitation of the spin wave and their manipulation and their eventual detection is known as magnonics. Okay, so that is just to get the nomenclature in place. Now, how did spin caloritronics really come into play? The emergence of spin caloritronics can be looked upon as the triangulation of three core areas. Okay, so one, of course, is charge currents itself, and in addition to that, you have the area of thermoelectrics. So thermoelectrics, Manoj was telling me that you're probably going to have some lectures on thermoelectrics. So how are thermoelectrics important? Thermoelectrics is important because what one tries to do in the area of thermoelectrics is to use thermal gradients to generate a voltage. So it is basically a tool of energy harvesting. You have waste heat in a number of physical processes, like it can even be your automobile engine, which generates a lot of waste heat. And the question is, can one harvest that waste heat to usable forms of energy? And that is how the area of thermoelectrics came into being. Now, if this material which you're trying to use also has a magnetic element to it, then you're looking at magnetothermal electricity. Okay, and that is where spin caloritronics comes in. So when you have a thermal gradient giving rise to a charge current, what you're looking at is normal thermal electricity. When you have a thermal gradient giving rise to a spin current, this is known as spin pumping. Okay. Now, a spin current cannot be directly measured off, and to measure that, you need to use some other phenomena. One of the phenomena is inverse spin Hall effect, and by doing that, you can convert a spin current to a charge current. So you have these three phenomena which kind of go hand in hand as far as this area of spin caloritronics is concerned. Okay. Now, let's start at the very basic. If you take a simple metal, and I know if I have a simple metal like this, I apply a delta T, that means I apply a temperature gradient at the two ends of the metal. What do I get? I get a flow of heat current, right? That flow of heat current is basically described here. So the resistance to that heat current is what basically defines your thermal conductivity of a solid. Okay. Instead of a delta T, if I was applying a delta V, that means if I was applying a potential difference, then the resistance to that is basically measured by the electrical conductivity. Actually, it's inverse, the electrical resistivity, right? And these two terms are intimately related to each other through what is known as the Wiedemann's-Franz law. So, which in the case of simple metals, the ratio of these two is a constant with the goes as L by T, LT, where L gives you a Lorentz factor. And so this is something which is a set universal constant, at least as far as simple metals are concerned. However, they do break down, especially in the vicinity of phase transitions, or if you have very strong electron correlations. If not, electrical conductivity and thermal conductivity go hand in hand and are intimately connected with each other. Now, another area, a related phenomena which one has to bear in mind is thermopower, or what is the Seebeck coefficient. So if I take a metal and I apply a temperature gradient, that means I put T1 and T2, which are dissimilar at two ends. I also get a voltage out of this, right? This is how your thermocouples work, for instance. You take two dissimilar junctions and put it together, and you can draw out a voltage out of this. And that voltage is characterized by what is known as the Seebeck coefficient, which goes as del V by del T. And the Seebeck coefficient, again, is an intrinsic material parameter. Every material will have its own Seebeck coefficient. Every metal or semiconductor will have a Seebeck coefficient. And that is something which, again, is used to characterize metals and semiconductors and a whole bunch of quantum materials, right? Now, so here, if you're looking at here, in this case, when I'm talking about charge and heat currents, I'm talking about a simple metal. Okay. Now, if this metal is magnetic, then what happens? Now, so for instance, take the example here. So I am looking at, say, a wire of maybe gold or aluminum or something which is non-magnetic, and I apply a perturbation, which can be a temperature perturbation, or even in most cases, it's an electrical perturbation. You're applying a potential difference between the two. And so what I have is a flow of current through that wire or my tube. Now, so in this case, you have a current, but the electron spins are not coming into picture, right? So what happens here is that on an average, if I sit at the end of that tube and count the number of electrons passing me by, on an average, I will have an equal number of upspins and downspins. Okay, so that means that I have unpolarized electronic current. So that is this case which is shown here. So in a simple metal, what happens is I have a unpolarized current. So I do have a large current, but since the total number of upspins and downspins are same, my effective spin current is zero. Okay. So now this was the case in a simple metal, like which is non-magnetic in nature. If I move on from a simple non-magnetic metal to a magnetic metal, then the density of states looks different. So in this case, what I have is something known as a spin split density of states, in which now you have two bands, one comprising of the upspin electrons and the other comprising of the downspin electrons, and there is a slight energy difference between the two. Because of this, you will have more of one kind being predominant. Okay. So if I look at nickel, cobalt, iron, these metals, and I do a similar measurement, and I sit at the end of that tube and look at the number of electrons which is crossing me by, and I average it out, I'll see that now it is not 50-50. It might be 60-40. I'll have 60 upspins and 40 downspins. So now what it means is that in addition to charge current, the charge current is still 100. I have 100 electrons crossing me, but now there is a difference between the upspin and the downspin. So I have an additional spin current, and I have a spin current in addition to the charge current. Okay. Now that is this case, so in which you have what is known as a spin split density of states. Now the third condition, which is a relatively rare condition, is one in which the spin split density of states is such that only the Fermi level crosses only one of the split bands. So that means the Fermi level is, in this case, is crossing, say, the upspin density of band, and it is not crossing the downspin density of band at all. So here, if I now sit and count the number of electrons which is coming out at the end of the tube, I will see that if there are 100 electrons crossing me by, all of them have only one kind of spins. So all of them are spin up, for instance. So in this case, now I have a good amount of charge current, but I also now have a full amount of spin current. So that means it's a fully spin polarized current. So this kind of materials in which you have a spin split density of states such that the Fermi level crosses only one of the spin split bands is known as a half metal. Okay. Now half metals are experimentally rare, but they are not completely unknown. Like for instance, some of the holdout manganites, LaSMNO3, for instance, is reported to be a half metal. You have a very famous case of chromium dioxide, CrO2, being a half metal. You have half metallicity in some of the half fusellar intermetallic alloys and so on. However, the problem is that many of them are not exactly half metals when it comes to room temperature operation. You will see half metallicity when which one goes to much lower temperatures. As one increases the temperature, there are a lot of scattering processes which does not conserve spin. And so they are basically spin flip scattering processes. So you have an up electron, it scatters and becomes a down spin. So then that much of spin polarization is lost. So nevertheless, this is something which has been known for quite some time, that you can have a finite spin current in magnetic solids and a larger spin current in half metallic solids. Now, our interest is on a different class of materials by itself, and these are not magnetic metals at all. They are magnetic, but they are not metallic. Okay, so what that means is that there are no free charge carriers for electronic conduction at all. So in that case, one can get what is known as a pure spin current. So which means that since there are no free electrons to carry your perturbation, there is no effective charge transfer across the solid. So your charge current is zero. However, you can still have the spin degree of freedom being transported across your solid. And so you have a finite spin current in the absence of charge current. And that happens because perturbations like heat or many other perturbations can also be carried by magnons, which are quanta of spin excitations. Okay, so this is known as pure spin transport. So the earlier two cases are known as spin dependent transport because here you actually have electrons which are moving and you're looking at the spin of those electrons. So they are spin dependent electronic transport. Whereas in the last case, you're looking at purely magnonic transport. There is no charge which is flowing in a solid. You only have the spin degree of freedom, which is basically a transfer of spin orbital momenta. This is a magnetically ordered solid, so you can actually have excitation of spin orbital momenta, which can go across the length of a system. And so this last case is a very special one, is operative only in the case of magnetic insulators and is at the heart of the area of magnetics. Now, why is this important? Why should one take the trouble of using spin current at all? The reason is simple. Charges interact very strongly with its surrounding. So, whenever you're looking at any kind of charge current, charges are an electron or absence of an electron, a hole. They interact via the Coulombic repulsion. They interact very strongly with its surrounding, and that interaction is what gives rise to resistivity and also dissipation of energy. And so that is the reason why, for instance, all our electronic equipment gets hot on you, right? So what is basically happening at the microscopic level is that you have electrons moving. These electrons interact strongly with its surroundings. It scatters with other electrons. It scatters with phonons, lattice defects, and so on and so forth. And by doing so, it dissipates its energy. That energy is dissipated in the form of heat, and that gives rise to Joule heating. And that is the principal energy loss mechanism at play. Becomes extremely critical as one goes to smaller and smaller sizes. On the other hand, if you're looking at a spin current, here a charge is not physically moving. Okay, all that you have is a transfer of spin orbital momenta. So the magnon is moving. This is not a fermionic entity, it is a bosonic entity. A magnon in general interacts very weakly with its surroundings. Okay, it does interact. Interaction is not zero, and however, it interacts very weakly with its surrounding. And since it interacts very weakly with its surrounding, the amount of dissipation is minuscule. Okay, so if you, in case you're looking at the phenomena of simple electrical resistivity or charge current, the length scale of the problem is defined by what is known as the electronic mean free path. So what is the electronic mean free path? Electronic mean free path is how much does an electron physically move before it encounters its first scattering event, right? It moves a few lattice spacings, it encounters a scattering event, and then it dissipates a bit of its energy. In the case of spin current, the length scale of the problem is defined by what is known as the magnon diffusion length. It's a different quantity. And on an average, the magnon diffusion length can be at least 1,000 times larger than the electronic mean free path. So what that means is a magnon will travel at least 1,000 times more before it encounters a scattering event. So now you can imagine why the area of magnonics is important, because here you are trying to use a mechanism of information transfer which is not fully dissipationless but effectively dissipationless, or at least 1,000 times better than charge transfer. And that is the reason why magnonics is important and people are very interested in this area of research. Now, before I go to the concept of spin current, and I've already talked about what a spin current is and so on. But I just want to remind everyone that though this area has developed in the recent past, this is something which we have kind of known since a very long time. So just let us look at electrical and thermally driven charge slash spin effects. Okay, please look at the phenomena on the left hand side. So We have all seen the standard Hall effect. So what do you have there? You have typically a non-magnetic metallic system or a semiconducting system. You apply a potential difference, and then you apply a magnetic field perpendicular to the direction of electron flow. And what you get is that you get a transpose potential difference, which is orthogonal to both the direction of the magnetic field and the direction of electron flow. So that is the standard Hall effect as it is given here. So that means you have a finite H is not equal to zero. You have a finite magnetic field. This is a non-magnetic system, so magnetization is zero, and then you get an Hall effect. Now, if instead of a non-magnetic system, I was looking at a magnetic system, then I get something which is known as the anomalous Hall effect. That means that the magnetization is now non-zero. So in when this case, when the magnetization is non-zero and I pass an electric current through this solid, I actually don't even need to apply an external magnetic field. I still get an Hall effect. In the absence of an externally applied magnetic field, I can get an Hall effect, and that is known as the anomalous Hall effect. First approximation is directly proportional to the extent of magnetization. Okay. Now here, an interesting thing happens. So the anomalous Hall effect can arise due to multiple scenarios. The most relevant, at least in this context, is something known as asymmetric scattering. So if I have an electron which is coming and it has an upspin, what it does is it sees a local magnetic moment and it scatters from that magnetic moment. Okay, in this case, if electron is an upspin, it sees a local magnetic moment, it scatters. Now, that local magnetic moment will also have either an upspin or a downspin because it's a magnetic moment, right? Now, when it is an upspin or a downspin, the effective scattering cross section is different. So you will have not equal scattering cross sections. And so this is schematically shown here. I have an upspin going here. All my upspins will go here, whereas my downspin will go here because it has two different scattering cross sections now. So in the absence of an applied magnetic field as well, in a magnetic solid, I can get an anomalous Hall effect, which means that depending upon the sign of my incoming electron, I have two different crossing sections. What that does is that it gives me more upspins on this side of the specimen and more downspins on this side of the specimen. So what you see here is basically the first idea of a finite spin voltage. And you can see that there is a asymmetry in the number of upspins and downspins when you look at the two sides of a specimen. And that is the first emergence of really a finite spin voltage. Now, if I move from, say, a magnetic solid to again a non-magnetic solid, that means my magnetization is zero, but I move to a system which has large spin orbit coupling. In this case, the scattering site, which is now a site which has large spin orbit coupling, basically mimics the presence of a magnetic moment. Okay, and I'll leave the details from now, but what it does is effectively the same thing. And this is known as a spin Hall effect. The spin Hall effect, again, the same thing happens. You have more upspins on one side of the specimen and more downspins on the other side of the specimen. And so what this basically gives you is a concept of an effective spin voltage across the specimen. Now, these are all electrically different driven effects. The Hall effect is an electrically driven effect. You can also have thermally driven effects, and you have actually one-to-one correspondence in this case. So instead of the Hall effect, you have something called a Nernst effect. Instead of the anomalous Hall effect, you have an anomalous Nernst effect. Instead of a spin Hall effect, you have a spin Nernst effect. Basically, the same phenomena at play, the only difference being that instead of applying a delta V or an electrical potential difference, one would apply a temperature difference. So, so this was the introduction. So the area of spin color electronics actually started in 2008 with a landmark paper from Tohoku University in Japan, Ken Uchida and gang, who were the first ones to realize. So it's actually quite interesting. You see, the Seebeck effect has been known for more than 150 years. It's a very old effect. People have been knowing about this for ages. It took them 150 odd years to realize that there is a spin equivalent of it lying around, you know, in our immediate surroundings. So what Uchida and his PhD supervisor Saito realized is that instead of a simple thermocouple like system where if you take a simple metal and apply a delta T, you will get a voltage. If you take a magnetic metal and apply a delta T, also you get some kind of a voltage. The only difference is that it's not an electrical voltage. In this case, it's a spin voltage. You're not looking at an electrical current, but you're looking at a spin current. Now, the problem is we are used to measuring electrical. How does one measure a spin current? As I said, you have an asymmetry in the number of up spins and down spins on either side. This is all fine, but how does one measure it out, right? So the way to measure it is through something which is known as the inverse spin Hall effect. So I have shown you the spin Hall effect in one of my earlier slides here. So what I'm doing here is that this is a non-magnetic metal which has large spin orbit coupling, and it basically gives me a differentiation between upspin and downspin. I use the inverse of that. So basically, when I have a charge current in the presence of large spin orbit coupling, it gives me an effective spin current. This is the spin Hall effect. The converse of that also exists, which means that I have a spin current and I pass it through a system which has large spin orbit coupling. It gives me now a charge current. So this is known as the inverse spin Hall effect. And this was also a discovery from the very same group a couple of years before that, where they showed that by just using paramagnetic metal which has large spin orbit coupling, one can convert a spin current to a charge current. And this is the phenomenon of inverse pinhole effect, and this is the standard in this area. If you need to convert a spin current to a charge current, this is what you basically do. You take your magnetic subunit, you cap it with a layer of a high Z element like tantalum, tungsten, platinum. It has to be non-magnetic and it has to be a high Z value. And then you basically get a voltage on the conversion of your spin current to a charge current. So this is how the spin Seebeck effect and many other associated spin current effects are actually physically measured, because now you can measure this out in the form of an electronic voltage. We are used to measuring voltages and currents in our labs. This is the way to do it. So the first observation of the spin Seebeck effect was by using what is known as permalloy, which is iron nickel based soft ferromagnetic alloy. And what they did was the following: they took a slab or a thin sheet of permalloy. They applied a magnetic field. So you saturate the magnetization. You apply a delta T temperature gradient. When you apply a temperature gradient, you now have a flow of spin current in this direction. This is shown as JS here. And then what they do is that they put two thin pads of platinum on top. If you see this, okay. What happens is that the spin current goes, it encounters this bar of platinum. At the interface, it then converts from a spin current to a charge current through the inverse spin Hall effect, which I mentioned earlier. And that now gives rise to a finite potential difference. So if I take a voltmeter and I put it across these two ends of the platinum bar, I actually get a voltage. Okay, I go to the other end, I get a voltage in the opposite direction. If there is no platinum or tungsten, in this case it was platinum, there is no platinum, I actually don't get a voltage, which is shown here. So this clearly shows that you need this spin to charge conversion device to convert from a spin current to a charge current. And this was how the first observation of the spin Seebeck effect was actually done. Now, they then followed it up with a number of interesting measurements to verify it. Look, this is basically the coercivity of the magnet. I'm not sure how many of you are very aware of magnetism, but hysteresis is something which you all would have heard of. The spin Seebeck effect has a particular dependence on the magnetic field. So if you change the direction of the magnetic field, you expect a sinusoidal dependence, and that is what was seen here. What is the location of the spin to charge conversion layer also determines the magnitude of the spin to charge conversion current or voltage, and that is seen here. So all of this was kind of measured for the first time and demonstrated by Uchita's group in 2008. It was a landmark paper in that area. Now, the problem was that this created a lot of excitement. We were very happy. Oh, we are finally seeing spin current. But this is a magnetic metal. So since it's a magnetic metal, one is quite sure that though we are measuring out a voltage, one cannot rule out the contribution of a charge current also adding up to a voltage, right? So as I showed in some of my earlier slides, the key in magnonics is to look for systems which are magnetic insulators so that there is no contribution at all from the charge current part and you're only looking at the spin current. So this was a criticism against this work, and so the same group then took 2 years to solve this problem once and for all. And so they what they did was to move from permalloy to a material class which is known as a garnet. It's an oxide. This one was a lanthanum yttrium iron oxide. This is a ferrimagnetic insulator. It has a robust band gap, more than 3 electron volts. So at room temperature, you try and measure the resistance across it, you see an overload. There are no free charge carriers around at all. And they basically just did the same measurement all across, all over again on this system, and they showed similar results. So this is the same here. When you measure the voltage across one of the platinum pads, you see a voltage like this. You measure across the other one, you see a voltage like this. And so basically they repeated the same experiment, this time in the absence of conduction electrons. So this was then the first real robust demonstration of a true magnetic spin current. So here there are no free charge carriers, there are no electrons to contaminate your signal. So what you are actually seeing is magnons moving and getting converted to a charge current which you measure out, right? So this was then the first real observation of the spin-Seebeck effect, which is purely magnon driven. Ever since that time, this class of materials, which Uchida had grouped, which is known as a garnet, has been model systems for looking at many kinds of spintronic and spin electronic phenomena. So, like for instance, a very popular member of that system material class is known as yttrium iron garnet, has the formula Y3Fe5O12. So this is a ferrimagnet. So that means it is anti-ferromagnet-like, but it has a finite magnetic moment because there are two dissimilar moments which are opposite to each other. And with a large TC, so it has a transition temperature of 560 Kelvin, well above room temperature. So at room temperature, it is magnetic, it is insulating, and it is ideal for all kinds of spin-Seebeck effect measurements. So now, as I said, Uchida's group pioneered this work, and this configuration on the right is something which you would remember from the earlier slides, and this is how they did their initial set of measurements. Okay, so there are two measurement geometries in which spin-Seebeck effect measurements can, in principle, be done. So the way in which the field evolved was it first started out by using what is known as a transverse configuration. Don't worry about the names, but this is how the first set of measurements were done. But people realized that the transverse configuration could have some other experimental artifacts. So people have now moved on to what is known as a longitudinal configuration. So here what one does is does not make a slab like this. You look at a magnetic slab, you put a longitudinal spin to charge conversion layer on top, and now you apply a delta T across this. Okay, you apply delta T in this direction, and you get a voltage here. So this is known as the longitudinal configuration, and as a matter of fact, ever since that time, almost all spin-Seebeck measurements are done in this configuration to such an extent that now, if you look at spin-Seebeck as a phenomena, people actually just call it the longitudinal spin-Seebeck effect. It's called the LSSC because the transverse one could have artifacts. So that is something which has now become the industrial standard of sorts. Now, however, as an experimentalist, you have to be careful when you are looking at any such subtle signatures. And so then very soon enough, people realize that can these longitudinal spin-Seebeck effect measurements itself be contaminated? And the reason is the following, that this one schematic on the top is how one would typically measure the longitudinal spin-Seebeck effect. I showed you in the previous slide as well. I have my magnetic unit here in gray. I put a spin to charge conversion layer like platinum or tantalum or tungsten, some high Z paramagnetic metal on top. And in light blue, I apply a delta T in this direction and I get a voltage across this metallic layer. All this is fine, but this is exactly the same geometry you would use, for instance, for measuring what is known as the anomalous Nernst effect. Okay, I briefly alluded to this in one of my earlier slides, but let's not worry about the details at this point. Now, so if your system has an anomalous Nernst effect, then that voltage would add on to the spin speed voltage. Okay, so what that basically means is that if your system, magnetic system, is a very robust insulator, you don't need to worry at all. All that you will measure is the longitudinal spin Seebeck effect. But if your magnetic subsystem is a magnetic semiconductor or dirty metal, then the total voltage which you measure will be a combination of your spin Seebeck voltage and your anomalous Nernst voltage. And that is something which you would need to take into consideration. Okay. So there were other artifacts which people initially thought could arise due to the nature of platinum and so on, which have all been laid to rest. So at around 10 years back, everything in about 5, 6 years from the initial discovery, most of these problems were sorted out. That then left us with another key problem. The problem was that what is this a interface phenomena or a bulk? So that what basically it means is there a thickness dependence? So I showed you, I have a magnetic system. I put a metal to insulate metal layer on top. Now, is it looking at the magnons only from the interface, or is it looking at the magnons from the bulk as well? So this was a question which was important in the context of spin Seebeck. And so basically what it means is there a thickness dependence? So then people did this by doing careful measurements by changing the thickness of these magnetic units. So this is a ferromagnetic insulator. This is a normal metal. I am applying a delta T and I'm pumping magnon current, which at the interface gets converted to an electrical voltage. So what I do is I do this measurement with very different thicknesses of my magnet and try and get a sense that what is happening to my spin Seebeck voltage. So the measurement would look something like this. So basically what it shows you is that after some point, the signals saturate. Okay. So that then reassured the community that, okay, so what is happening is that the length scale, and this is something which I've talked earlier in my listing, that the length scale here is actually dictated by the magnon propagation length. So if my thickness of my magnetic unit is smaller than the magnon propagation length, then all my magnons are getting used up. It is essentially a bulk phenomena. However, if my thickness of my magnetic unit is larger than the magnon propagation length, then the magnons from the real way back is not going to reach my interface because I have a much longer path to traverse. So in that sense, it is a bulk quantity, but with the boundary conditions being defined by the magnon propagation length. Now, in the early days, people then started doing, why, how could this be used, and how are magnetic spin currents useful? So, for instance, people did spin Seebeck measurements and say that okay, this really follows the magnetization of the sample. But there are easier ways of measuring magnetization. So one doesn't really need a spin Seebeck measure to get a sense of magnetization. Here is another interesting thing on the right hand side, which is people were looking at multi-layer specimen. You have one magnetic unit, another magnetic unit, and then the spin to charge conversion layer on top, and they're trying to see that, oh, how does my interfacial magnetic unit behave? Can I tune it, and so on and so forth? So there have been a lot of, and there still continue to be a lot of very interesting work happening in this area to try and get a sense of whether these spin currents, because you see, the thing is this: you have a spin current, but how does one manipulate that spin current? Because what one is trying to do in this area is to try and play a game similar to what happened in electronics. You had, of course, we knew that in a semiconductor you could pass a finite amount of current. But then the real advances happened when we started making diodes and transistors and so on and so forth. So the idea here is to try and make similarly things like spin diodes and spin transistors and spin logical units so that you can now have systems which do not heat and have ultra low dissipation, low power devices, right? So not just that, and that is from the application point of view. From the uh, pure physics point of view, there are lots and lots of interesting things which happen here. For instance, here is an example from exactly a decade back now, which shows how a magnon interacts with a polaron. So these are different quasi-particles in solids. When they start interacting with each other, you can actually get signatures of it in the way your spin currents behave. So the spin currents can themselves be a microscopic probe of both quantum materials and different quantum mechanical phenomena. And that is the takeaway message here. Now, how does one generate spin current? So in this case, I have talked about the spin Seebeck effect. So which means that I am generating a spin current by applying a temperature gradient. But that is not the only way in which one can generate spin currents in solids. You can generate it through a number of techniques. So what I have been talking so far is this one, because that is something which is closer to my heart and I do it in my lab using a temperature gradient. But that's not the only way. You can shine microwave, for instance. You can use electromagnetic wave application. You can apply electric fields. You can use spin orbit effects. You can inject spins. You can even do mechanical rotations or use of other geometric phases to drive spin currents in solids. So this actually gives you a wide array of means to generate spin currents. And this is important because if one eventually at some point reaches a device level, it would be interesting to see which one is the most efficient means of generating spin currents in solids, right? And there has been a fair bit of progress in this area. Like for instance, I'm showing you I forgot to put the reference here. So this is a paper from a few years back where they have shown the first set of magnonic circuit elements. So what they did here was to make a spin wave NAND gate on the left side and also a spin wave multiplexer on the right. So as you can see, now we have moved to a NAND gate as a universal gate. So you have moved to gate operations using magnons. They have also moved to multiplexing operations using magnons and so on. Now, so another real interest. So this was about purely magnon-driven systems. Another real interest when it comes to quantum technologies is magnon-based hybrid systems. So magnons, as I said, interacts relatively weakly with its surroundings as compared to charge carriers or charge currents. However, its interaction is not zero. And so magnons can interact with other quasi-particles. It can interact with phonons. It can interact with photons. It can also interact with whole superconducting qubits. So magnons coupled with these kind of quasi-particles can gives rise to a number of different device architectures which can have utility in real-world systems, especially because they are ultra low dissipation platforms, and that is the reason why magnons have a lot of promise. So if you look at magnon-based hybrid systems, there are a large number of both materials and architectures which are being thought about. So you have magnons, as I said earlier, interacting with phonons, with fluxons, which means superconducting qubits, with excitons, with plasmons, with photons, and you have many of them being important for quantum computing. There are actually also Magnon qubits which are being made, but they are still at a lower level. What they seem to be more useful for is actually coupling with superconducting qubits and using the Magnon conduits as a readout mode. And that there it has some benefits over existing technology. Also, Magnons are like if you look at the band structure of solids, you have an ek phase diagram, like, and so magnons are also similar. So there is an energy and a wave vector associated with a magnon. Magnons typically operate at much higher frequencies, so you're basically looking at the gigahertz to terahertz operating speeds, and that then gives you the flexibility or the option of coming up with ultra fast devices. So that is another major area of interest. You can combine it with external perturbations like magnetic field, electric field, surface acoustic waves, and so on and so forth. So this is a very relatively new but very exciting area of research with lots of possibilities. And basically, at the heart of all of that is a magnetically ordered insulator, and we literally know many thousands of them. The question is, how does one harness these magnons to come up with reliable low power functioning for our own use? So here are two other examples which are directly relevant to quantum technologies, for instance. So people have shown quite a few years back magnon entanglement in a hybrid magnet cavity system. So here what they did was to create a microwave cavity using two YIGs, yttrium iron garnet, so using two yttrium iron garnet spheres, and they made this into a coupled microwave driven cavity and showed magnon entanglement. This is a very key quantum mechanical attribute. More recently, they used a non-reciprocal magnetic waveguide to look at unidirectional spin readout from a plasmonic, a fluxonic superconducting qubit systems. So here again, what you have basically is a magnon coupling to a superconducting qubit. So these are lots of interesting areas in the horizon. So now, as I said, the Seebeck effect was discovered 150 years or so back. The spin Seebeck effect came in much later. It took full 150 years for us to move from the Seebeck effect to the spin Seebeck effect. Once the spin Seebeck was discovered, people realized that almost all the thermal effects which happens with electrons will also happen with spins. So as a matter of fact, these are two, more recent papers. This is the spin Peltier effect. This is the Mank-to-Thomson effect. So it's quite interesting that even fundamental effects like this are now being discovered in this day and age, because you would have think that when people tell you that most of physics is known and most of physics effects are also known, you can see that that is certainly not the case, at least when it comes to some platforms like Magnon. So the Mank-to-Thomson effect was discovered again by Uchida's group uh, just half a decade ago, and there are a lot of interesting work again happening in these areas. Now, well, this is something which is uh, especially interesting for me, and that is to looking for superfluid spin currents. So now, when you look at Magnon spin transport in solids, so I told you that the length scale of the problem is defined by what is known as the Magnon diffusion length. So the transport is diffusive; it is inherently lossy. Now, the question is that in electronic systems, we know that there are superconductors, which means under certain material classes, under certain temperature and doping and other conditions, you can actually have Cooper pairs which move electrically without any electronic dissipation, right? You have a superconducting state in electronic systems. The question is, do you have an equivalent of it in the spin system? So when you say you have electronic current and you have superconductors, can you have spin currents and spin superconductors? Or in this case, it is not called a superconductor, it's actually called superfluidity. So in a normal system, this kind of system which I have talked about so far, you inject a spin and it will die down like this. And so this is the standard medium. But if I have a system which has spin superfluidity, I inject a spin, it will live over a much longer distance, and then you can detect it out. So as it is, magnons, by virtue of their larger magnon diffusion length, give you a few orders of magnitude advantage over electronic systems. On top of it, if you move to superfluid spin currents, it can actually give you many orders more in terms of advantage. And it then also makes it possible to try and look like phenomena like spin-Josephson effect. So electronic Josephson effects are at the heart of superconducting qubits. Now, if you have a spin-Josephson effect, you can actually try and make a completely magnon-based qubit, which can work at significantly higher temperatures. So for instance, if you have a qubit architecture which does not require a dilution refrigerator, for instance, you suddenly make it much more attractive and easily doable. So that is another major focus of research, and it is some people along are seeing it. So far, there has been only one real, or maybe two real examples of it. So one was in a very strange system, chromium dioxide, Cr2O3. So if you look at Cr2O3, this was a paper in Science Advances a few years back. And what they showed was that below around 20 Kelvin, they see a very sharp rise in basically what is effectively the spin current. And when they do a distance dependence on it, and they'll see that you have a long-lived spin current which mimics what we would expect in a spin superfluid state. And so what I want to draw your attention to is to this. Look at how long the spin currents are traveling. It is traveling here to a distance of 20 micrometer. Compare this with how much does an electron travel in a normal metal. In a normal metal, the electron would travel at best a few lattice spacings. Even if it travels like 10 lattice spacings, you're looking at what, 100 angstroms, something like that, right? On the other side, you have something which is moving quite easily to 20 microns. So this is the kind of advantage which magnon transport can give you over charge transport. The other thing, which is from Hillebrand's group in Germany, was that they used a kind of different technique to look at ferrimagnetic YIG again, and they created a Bose-Einstein condensation of magnons at room temperature itself. And they also showed what looks like Josephson oscillations. If you look at these graphs here, let me know go into the details of it. But these are the first signs so far that you can actually have a spin Josephson effect like you have a charge Josephson effect. The only problem is that here you can see that the time scales are much smaller. So this whole measurement is of the order of a few hundred nanoseconds. So these time scales are not enough. But this here, you should remember, is happening at 300 Kelvin. So at 300 Kelvin itself, you have now signatures of Josephson oscillations. Though the fact that the time scales are small is a problem. But this now gives you a lot of avenues to play with. Hillebrand group in Constance is one of the leading groups in the world who works on this, and we're looking forward to more interesting results from their side. Now, so I will summarize this part here. So I hope the key takeaway message, and I hope some of you would appreciate it, is the fact that magnons, which are the quanta of collective spin excitations, can have very distinct properties which make them an appealing candidate for a number of different applications. Magnons can couple with other quasi-particles or other excitations and can give rise to a host of hybrid device possibilities. So you can have magnons coupling with photons, phonons, other magnons, and so on. And this gives rise to a number of different playgrounds for us to play with when it comes to applications. And there has been a significant amount of progress in the last few years. And before just finishing, I'll show you a device, an apparatus which we made for doing spin caloritronic measurements in our place. This is not a very expensive apparatus. All that it requires was a closed cycle refrigerator coupled to a locally procured electromagnet. The signals were small, so we had to put it inside a Faraday cage and so on. And we used this for our spin civet measurements quite a lot. So Manoj, if it's okay, I think I should probably stop here and take questions because I didn't want to go into a lot of my own research. Would probably stop at the introduction of this thing itself. Is that fine?
Yes, sir. If there are any query related to that, then it will be good to include those discussion into the part.
Sure, sure.
Yeah. So I will first read the queries for this class and then to the previous one.
Sure.
So, sir, many people are asking for some reading material and references apart from the PP copy of the PPT. It will be better if you can suggest some study material, or we can post it in the class shared with all the participants. If you can share with
I
us.
can see there are multiple good reviews on magnons or magnonics and spin electronics which are available. I can share it with you. One thing which I would even suggest people to look at is if you can go to they can go to archive. There is also a yearly in the past couple of years there has been JPCM publishes what is known as a magnonics roadmap. Okay, so that is a very good place to look at. But I can share this with you. That is okay because I don't
Yes,
remember the
sir.
reference.
So we will post it along with the copy of the PPT. So
Sure.
from this lecture from Veeramanikam M, kindly show that prototype product and explain.
Which product is he talking about?
Which product? I think possibly
Well,
the setup, maybe the last one. Possibly the setup. I think
is
you
he talking about this one or the setup?
setup, maybe. I think.
He had just
He
written
had just
some.
written some.
You're talking about the setup? Veeramanikam
Setup,
is a yeah,
yes, sir.
yes,
Yes, sir.
yeah, yeah,
He confirmed
yeah,
the
yeah.
setup. Yes.
Sure. So this is how the setup looks. So this is a closed cycle refrigerator, which basically gives us a low temperature stage, because we are interested in quantum materials, so we do quite a lot of temperature dependent measurements. And this is how the sample holder assembly looks like. So basically, it has two blocks, because you have to apply a delta T. So you basically have two blocks in which between which you sandwich your specimen, and you have independent heaters and temperature sensors on both sides, so that you can make a well-defined delta T and accurately measure it. Okay. And so within our setup, for instance, we can give a delta T of up to 20 Kelvin. Anything beyond that is not possible, because these are in close proximity to each other. So a delta T of more than 20 Kelvin then just diffuses through. So we can get from 0 Kelvin to 20 Kelvin delta T. We can apply very small magnetic field because it's a small magnet in this case. And the devices which we use are either they can be polycrystalline specimens or single crystals or thin films. So all these three kinds of these things we have used. Now, one of the problems was, at least when we started, at least the first problem which we tried to tackle in that kind of systems, the signals are very small. So what we realized is that we had to make this kind of an arrangement where the whole apparatus, including the nanovoltmeter, which is used to measure the voltage, was inside a Faraday cage. So by doing this, then we could actually get a very good data. Let me show you. So like for instance, these are all spin Seebeck data. Okay, let me show you another one. Yeah. So this is the temperature dependence of the spin Seebeck in this case. So to come to this kind of signal to noise value, so we had to move this Faraday cage and so on. We took a few years to get an absolute hold on this. This we published this in 2020 in PRL, and yeah. So yeah, so that's how the apparatus per se looks like. So the device geometry is typically like this. In this case, it was LCMO. So you have a lanthanum oxide substrate. We had a 200 nanometer LCMO thin film grown on top of it using pulse laser deposition. And then you deposit a 10 to 13 nanometer thick platinum layer, which acts as the spin to charge conversion layer. And then you measure the voltage across this. So this is the device geometry. Yeah.
Okay, sir. So there were some queries left for previous lecture. Please explain charge ordering.
Okay. So let me say that with the example of a doped manganate system. Okay. So the parent manganate system is called LaMnN3, lanthanum manganese oxide. It's a perovskite. Okay. So oxygen is always 2 minus, lanthanum is always 3 plus. So in the case of LaMnO3, all the manganese is in a 3 plus valence state. So all the manganese is in 3 plus, everything is hunky dory. There's no problem. Now, the moment you start doping holes, and you typically do that by doping, say, something like calcium, barium, or strontium on the lanthanum side. So calcium, barium, or strontium will be 2 plus. Okay. So if I'm putting, say, 30% of calcium in the place of lanthanum, now my Mn cannot remain 3 plus alone. I'm putting 30% of calcium. So now, in addition to my Mn3 plus, I will have 30% of Mn4 plus. Okay. So this is known as hole doping. By changing my A site ion, I change the valence of my magnetic element, which is manganese in this case. And that is how these systems are now called as mixed valence magnets. Now, suppose I dope 50% of calcium in my lanthanum side. So that means I have lanthanum 0.5, calcium 0.5. So now my manganese, which was initially all 3 plus, is now 50% 3 plus, 50% 4 plus, right? Now, what this does is not always, but in certain phenomena, in certain cases and at certain temperatures. So I have to arrange my 50% manganese 3 plus along with the 50% manganese 4 plus in my solid. So one of the ways in which it is done, I mean, I do not do this, the system does it, is that what it does is that it will have, say, a chain of Mn3 plus, followed by a chain of Mn4 plus, followed by a chain of Mn3 plus, followed by a chain of Mn4. So what is now effectively happening is my charges are ordering. Okay. That is what is known as charge ordering. That's the most simplest case of charge ordering. 50% of one charge state, 50% of another charge state at some temperature can give you a well-ordered, charge-ordered state. So that is how one would look upon charge ordering. It need not necessarily always happen at 50%. It can also happen at 25% in some cases, even smile, but it has to be some kind of a fraction, because if it is like at 25%, what that basically means that you will be having three of one kind and then one of the second kind, three of one kind and one of the second kind. So, so in that sense, it has to be an integer ratio of charges. So when you have that kind of mixed valence, two different kind of charges in a solid, then depending upon what your U is, what your W is, and so on, you can get this kind of a state where charges self-order within a solid. And that is known as charge. Yeah, you are muted, Manoj. Manoj, is there anything else? You're on mute.
Okay. How Mott insulators form quantum material?
Uh, okay, that's a strange question. I wouldn't say that Mott insulators form quantum material. Mott insulators uh, are themselves quantum materials, because what do you mean by quantum materials? When you say something is a quantum material, that means that you have quantum mechanical processes which is driving the ground state of those systems, and Mottness is one of them. Mott system is an effective quantum attribute. So it would. So that is the question should not be how can a Mott state form a quantum material, because a Mott state is a quantum material.
Yeah. So thank you, sir, for clarifying this. And we have come to an end. I think there may be some more queries. Possibly, the participant can email directly to you, and if possible, please resolve. And
Sure.
with this, I would like to thank uh, our today's expert. Thank you, sir. Thank you very much. It was really nice to see you for 2 hours, or more than 2 hours, actually. And yeah, possibly uh, mm, we will also have some more talks uh, from